In this slide, we talk about calculating the magnetic force on a current carrying conductor. In the previous slide, we had studied the Lorentz force acting on a single positive charge. We found out the formula for calculating the value of Lorentz force and also using the Fleming's right-hand rule to find out the direction of Lorentz force. Now, in this case, because we're talking about a current carrying conductor, we'll keep in mind that a current carrying conductor is actually carrying positive charges in the direction of current. So we have current. If we know the current direction, this is the same as the velocity direction, because that's where the positive charges travel. And so let's assume that there is a length L of a wire which is carrying current I, and this length of wire is present in a magnetic field B. Such a wire will experience a magnetic force or Lorentz force given by this equation. In this equation again, theta is the angle between the current and the field. In this, theta is very similar to the previous theta that we saw, because current is nothing but the direction of velocity of positive charges. So they are analogous. The directions are same direction wise. So the theta definition is still the same. Now in this example, I show you a picture of a magnet with north and south pole, and the magnetic field shown in the magenta color going from the north pole to the south pole, and there is a circuit in which current is flowing like this through the battery power supply, and there is a section of wire inside the magnetic field, and the current is sort of coming out towards from the screen towards us, and shown by this I. Important quantity to note is L. L is the length of the wire which is inside the magnetic field. It is not the length of the entire wire. Now for this, we are able to calculate the magnetic field using the magnetic force using this formula. Now to find out the direction of the Lorentz force, we use the Fleming's rule. We'll extend our right palm and then have the thumb point in the direction of current, and current is the direction of positive charges flow, shown here, and then we'll have the index finger point in the direction of magnetic field, which is on the x-axis, and the middle finger will point towards the Lorentz force. So Lorentz force actually pushes this wire upward. So only the wire which is inside the magnetic field experiences this force. Let us do a problem of calculating the magnetic force on the current carrying wire that was presented in the previous slide. As you see here, the field which is present is given to be 1.5 Tesla. So that's the strength of the magnetic field inside the region. And the length of the wire which is present in between the magnets is L, is given as 5 centimeters, and the wire carries a current of 20 amperes. So by looking at the direction of current and the direction of magnetic field, we can say that the sine theta is 1, because theta is 90 degrees. And then by using the formula for calculating the magnetic force, which we saw in the previous slide, we have I to be 20 amperes. The length of the wire which is inside the magnetic field is 0.05 meters, and the strength of the magnetic field is 5 Tesla, and this is sine 90. So this is fairly simple calculation, and that gives us the magnetic force to be 1.5 newtons. And remember, we already discussed the direction of Lorentz force on the wire is along positive y-axis using the Fleming's rule. So that is already was explained in the previous slide. This slide shows another interesting problem, which is a little bit more involved, because here we are calculating the Lorentz force on the black wire because of the field generated by the red wire. Let us see how the problem is stated. Your laptop connector cable is a pair of wires, usually red and black, packaged together along their length. Let's assume that the two cables in your laptop connector cable are separated by 1.2 centimeters. This is an important number that we're going to use because this number will be helpful in finding out the magnetic field. Along with their 4-meter length. So this is the length of the wires. So this length is useful in calculating the Lorentz force. Remember, the Lorentz force has a length term. So this is where it will be useful. While your laptop is charging, each wire carries a current of 3 amperes. So this is another important parameter. So the black wire carries a current of 3 amperes to the left, and the red wire also carries a current of 3 amperes to the right. The question is asking the magnitude and direction of Lorentz force. So Lorentz force is another name for the magnetic force, and the question is asking for the Lorentz force acting on the black wire. So that's the specific question. Let us see how to answer this question. First, we want to note that both wires produce magnetic fields in their respective surroundings. So because each wire is an individual wire, it will produce its own magnetic field in surrounding. As the current through both wires is the same, the magnitude of magnetic field produced by the red wire at the location of the black wire is equal to the magnitude of the magnetic field produced by the black wire at the location of the red wire. So essentially we are saying that the field produced by red wire at the location of black wire is the same as the field produced by black wire at the location of red wire. Why should that be true? Because we have seen the formula. The formula is shown here. The magnetic field of a straight line is given by mu 0 I divided by 2 pi r. And r is the position, so in our case this will be r. R is the position where you're calculating the magnetic field relative to the straight wire. This is your R. And the current is same. So the magnitude of the magnetic field due to red wire at the location of black wire comes out to be this. That's the magnitude. After getting the magnitude of the magnetic field at the location of the black wire given by this value, then we will try to calculate the Lorentz force on the black wire, and we can do that by using some concepts here. The above magnetic field produced by the red wire at the location of black wire produces a Lorentz force. It produces Lorentz force because there's a charge flowing in this direction in the black wire. So that's the V direction of positive charges, and there is a magnetic field present at that location B. So we are able to calculate the Lorentz force on this wire using the equation we saw a few slides before. And so this is the formula for getting the Lorentz force on a segment of wire. Sine theta again turns out to be 90 degrees. Sine theta turns out to be 1 because the angle is 90 degrees. The current is going to the left, and the field we will see will be pointing into the screen. Once we put that formula for Lorentz force, we get this to be our Lorentz force. Now these are just magnitudes. Now we will talk about calculating the direction. Let us understand the direction of both the magnitude which is produced at the location of black wire and the Lorentz force experienced by the black wire. So using the right hand thumb rule, we are able to figure out the direction of the magnetic field produced by the red wire at the location of black wire. And the magnetic, using the thumb rule, we are able to see that the magnetic field points into the screen at the location of the black wire. You stretch out your right hand and the thumb and imagine as if you are gripping the red wire. Once you grip the red wire with the thumb pointing in the direction of current, which is shown by this direction, current direction, then your curling fingers will point inward at the location of the black wire, shown by the blue crosses. So these are fields at the location of black wire. So keep that in mind, and then we will use the right hand 2 rule or the Fleming's right hand rule to figure out the direction of the Lorentz force produced because of this field shown in the blue crosses. So the thumb points towards the right because the direction of current in the bottom wire or the black wire is right. I just noticed a mistake here. The thumb should point not towards right. So there's a mistake here. This is not right because in the bottom wire the current flows towards left. So let me make this connection here. In black wire, current flows to the left. So it should flow to the left. The thumb should point to the left, and the index finger, which denotes the magnetic field at the location of black wire, should point into the screen. And when we do that, we will see that the middle finger will point along the negative y-axis. So that's the direction of the magnetic field or the magnetic force on this wire. So we got the magnitude from the previous slide and the direction to be downward. So that completed our problem of calculating the magnetic force due to one wire on the second wire in its neighborhood.